after it has been launched.
Huge, huge, huge. Much more than point 0.4, right? You can just look at the chart. I mean, point 0.4 was way the hell down here. I mean, 1, and we're almost at 2.
Yes, of course, Gary eyeballing at data is far more precise than actually measuring it, but no, Goofy, you really need a pair of glasses. Okay, so let's go ahead and look at the graph visually. On the left side, you can see the graph with the 1 rubber band, and on the right, the graph with 2 rubber bands. I perfectly aligned both graphs. The orange line is aligned with 0 meters per second. The blue line is aligned with the maximum velocity of the 2 rubber band launch, and it is close to 0.2 meters per second. The green line is aligned with the 1 rubber band launch and is close to 0.15 meters per second. If it truly were twice as fast, the blue line would have to be close to 0.3 meters per second, and it totally isn't, you dumb fuck.
Way short, okay? I would argue. But it's clearly more than 0.4.
No, Goofy, it clearly isn't.
So you're in big trouble. I don't like the way he did this selection, right? He selected part of the thing down here. So let's just see if we can see that. Get rid of your little box. Yeah, see, we can't see. I think he selected the part that is still going up. So I don't even think his selection was valid at all.
Seriously, what the fuck is wrong with your eyes? Clearly the part that is going up is in the blue area that I marked. The part that Professor Rousseau marked is clearly a straight line. Jesus fucking Christ. And now let's have some fun watching Goofy struggling so badly to interpret the graph.
The number he's saying it is 1.392. Okay, well, I'm just saying it's obviously bullshit. All right, I'm calling bullshit. So let me just I'll go back to the damn charts and you just look at them. All right, so here's this value. So it's almost like a centimeter on my chart here. So the 0 is right on the line for the stupid video. This is the start line. And so then we'll just jump to the second version. And so the start line for this one is way down here, I guess. How come it's got this loopy thing in it? Yeah, that's way off. But anyway, look how far up it is. I mean, it's just bullshit. I call bullshit.
Open up your damn fucked eyeballs and take a good close look at both graphs, you blind moron. Can you see and understand what you're looking at? No, you can't because you don't want to see the truth. It hurts your eyeballs. Your eyeballs desperately wants to see your stupid predictions, but that just won't happen.
And look at this total distance from this point to this point is clearly twice the height from this other one. So you just cheated. Fuck. You just cheated. Look at this height. It's from here to here. It's like a centimeter from my point of view. I mean, you can see that, right? You can see that. Let's use a little pointy head. Come on. Right here, right? It starts, this is the flat part right there, that little flat bit. And so all you got is this little bit here. That's all the distance you got. That's all the velocity you got out of it, was this little distance. And this fucking liar, this fucking cheater, faked the experiment. He just faked it. And look how far up it is. It's twice the length. If I go from this base to this top, it's twice the length. What a fucking conniving liar.
This is the fucking 0 line for both graphs, you bloody idiot. Not this line. This is the minus 0.1 line.
There's no beginning. There's no flat line. There's no origin. Right? You can see that, right? There's no fucking flat line here. There's no origin here. There's no, oh, it's not moving.
All right, let's try to explain this very slowly in little baby steps, especially for Goofy. First, let's listen to this.
A trigger has been set up so that the computer will start recording as soon as the glider is 20 centimeters away from the motion detector.
So, this is a Vernier ultrasonic motion detector, and what we should know about this is that ultrasonic sensors have a blind zone, which is an area directly in front of the sensor where it cannot reliably detect objects. This occurs because the sensor needs time to emit a sound pulse and then wait for the echo to return. If an object is too close, the reflected signal returns before the sensor can finish its transmission, making it impossible to get an accurate reading. How the blind zone works. Transmitted pulse. The sensor sends out a burst of ultrasonic sound waves. Signal confusion. If an object is within the blind zone, the sound pulse can't travel to the object and back before the sensor is still in its transmit state. Echo not received. The sensor is unable to properly receive the echo because it's trying to simultaneously send out a new pulse or is still recovering from the previous one. As Professor Rousseau pointed out, a trigger was set up so that the software will only start to record as soon as the glider is 20 centimeters away from the detector. And in fact, Vernier motion detector cannot detect closer than approximately 15 to 20 centimeters. Look it up. We can see proof of this blind zone within the data that Professor Rousseau collected. On the left side, we see the table with the timings, positions, and velocities. As you can see at the very beginning, at timing 0.00 seconds, the detector seems to detect that the glider is 0.211 meters away from it, and it seems to detect that it has a velocity of minus 0.353 meters per second, which means that it thinks that the glider is moving towards the detector instead of away from it. As you can see, these negative velocities keep being negative until 0.20 seconds. Also look at the distances, they keep decreasing to 0.25 seconds. So until this point, it keeps thinking that the glider is moving towards the detector. But beyond that point, so just outside the blind zone, the data stabilizes, the distances start to increase, and the velocities are positive, meaning that it now detects that the glider is moving away from the detector. We see the same within the other graph. At the 0.00 second point, the distance is 1.94 meters. So it seems to think that the glider is all the way on the other side of the air track, and it seems to think that the velocity is minus 25 meters per second. And as you can see, all the way to the 0.40 second point, it seems to think that the distance is always the same, that the glider is always located at the same position, but right after that, the distances or positions are normally increasing with 0.7 centimeters per unit of time. So everything under the 0.40 second point was the blind zone where the detector cannot accurately detect the positions and velocities. There was no cheating, Gary. This is perfectly normal behavior for a motion detector. You are just an incredibly pathetic coward and evidence denier as always.